So we started discussion of superfields last time. And we introduced the concept of Grassmann coordinates. So the superspace is made of 4 coordinates, ordinary coordinates, and theta bar, alpha dot. 4 Grassmann coordinates. And we also discussed that supersymmetry acts as a translation in superspace. It shifts theta alpha to theta alpha plus epsilon alpha over anti-commuting transformation parameters of supersymmetry. Theta bar alpha dot shifts to theta bar alpha dot plus epsilon bar alpha dot. And 4 space-time coordinates x mu shift to x mu plus I times theta sigma mu epsilon bar minus epsilon sigma mu theta bar. And then we found differential operator representation for Supercharges q alpha and q bar alpha dot, which implement this transformation, which means I times epsilon q plus epsilon bar q bar acting on x mu theta and theta bar gives us I times theta sigma mu epsilon bar minus epsilon sigma mu theta bar epsilon and epsilon bar.
So in general the fields would be a function of all the those coordinates, and the Susi would be just a translation symmetry over there.
Yes. Okay. All right. So this is how these Q operators, I won't write those Q operators again because you have them there in notes. So they have a differential operator representation which acting on x mu theta bar would make shift in x mu by this amount, theta this amount, and theta bar this amount. And we found that the differential operators that we constructed, we checked, satisfy the Susi algebra. Today we'll introduce a concept of chiral supercovariant. Derivative. The Q's and Q bars that we specific representation, differential representation we constructed which implements this transformation commutes with Q and Q bar commute with ordinary space-time differential operator because they commute with P mu. P mu is essentially I times d mu. But commute or anti-commute with the spinorial derivative d alpha. D alpha was the shorthand for d by d theta alpha, or d bar alpha dot, which was the shorthand for d or d alpha bar dot. So the spinorial derivative does not commute with q's. So now can we construct a differential operator which commutes with q and q bar, commutes with q and q bar? A differential operator or differential operators which commute or anti-commute with q alpha and q alpha. This is the spinorial differential operators, spinorial. And those derivatives we'll call covariant derivatives. Now if I start with the variables theta, theta bar, and under supersymmetry transformations they become x mu, theta bar, which is, I'm writing the same thing again. So this goes into this. So if I change my coordinates and super coordinates, superspace coordinates, from this one to the transformed one, how does that affect spinorial derivatives? So let me write d alpha. I could also write d alpha as d theta prime beta d theta alpha beta d x mu prime by d theta alpha d by d x mu prime. So if I want to change this object into derivatives of the prime system, this is the rule I have. Now d alpha prime, d theta beta prime by d theta is simply delta alpha beta. So that gives me d by d theta. This is delta alpha beta. So that gives me d. Now this derivative is the derivative that acts on here. There's a theta bar here. Theta, only theta is here. So that will give me minus I sigma mu epsilon bar alpha d by d there's some, why did I put minus here? There was plus here. Is that okay? So d alpha in the unprimed coordinates is d alpha in the prime coordinates plus this extra piece. this already suggests that if I construct a derivative, covariant derivative, give it a name, capital D, which is d alpha plus I sigma mu alpha beta just construct a derivative d alpha plus this object. This is dot, this is dot. Then this rule right away tells me that this derivative will not change under supersymmetric transformation, because this object written as this and written in terms of the prime coordinates is the same. Now let's check that. For this d alpha, I replace this d by d alpha prime. This is the shorthand for this. Plus I times sigma mu epsilon bar alpha d by d x mu. That is the first part. Prime. And then second part here is I sigma mu theta bar alpha d by d x mu. This whole thing is what was d alpha, and this is the second term. Now derivative of x in unprimed coordinates and prime coordinates is same. So I could as well replace it by prime. D by d x prime x mu is same as d by d x prime mu. Now let me rewrite this again. Add these two terms. And rewrite this as that's exactly what is d alpha in the prime coordinates. So by construction, what we have done is we have constructed a derivative which in unprimed and primed coordinates is the same, and that's what we call covariant derivative. So similarly, one could construct d bar alpha dot up as d bar alpha dot plus I times sigma bar mu alpha dot beta theta beta d mu. That would also be by similar kind of an argument, a covariant derivative, which means this would be same in the prime coordinates. Now we have constructed two left-handed covariant derivatives and two right-handed covariant derivatives. This is indexed alpha down, this is indexed alpha dot up. We can lower and or raise these through epsilon symbols. So let me write that answer also for you. Now d alpha up from here is same as d alpha beta d beta. And write this here. So that gives me epsilon alpha beta d beta. That is d alpha up. Except that, remember the rules on spinorial coordinates, epsilons act unlike on the theta, unlike the coordinates, with an extra minus sign. So there is an extra minus sign. And then do the little bit of algebra and you'll find it is theta bar beta dot sigma bar mu beta dot alpha d mu. And similarly, construct d bar of covariant derivative with alpha dot down by epsilon alpha beta down d bar dot beta this. And the answer is minus d alpha dot bar minus I theta beta sigma mu beta alpha dot d mu. Now we have constructed these covariant derivatives and we also know their expressions with index ups and downs. We could ask the question, do they satisfy any algebra? And I think, is there an exercise? Yes. Exercise. That anti-commutator of d alpha with d beta is 0. Anti-commutator of d alpha dot d bar beta dot is 0, and anti-commutator of d alpha d bar alpha dot is twice sigma I sigma mu alpha alpha dot d mu with a minus. It's a straightforward exercise, it's not very complicated. Use these definitions and just, but you must have recognized that this structure is exactly the same as the algebra satisfied by supercharges. Same as the algebra satisfied by supercharges. So that's exercise 1. Exercise 2. Calculate the anti-commutator of Q with D and check that it's 0. And that's same as D alpha Q bar beta. That's same as D bar alpha dot Q beta. And that's same as d bar alpha Q bar beta naught. Means that these covariant derivatives, these derivatives that we constructed, anti-commute with Q charges. But that's nothing but the statement that they are covariant derivatives. That's the reason why these covariant derivatives in the primed or unprimed coordinates are the same. Because under supersymmetry they don't change. So all their commutated with supersymmetric charges are 0. So that's a restatement of what we said here. So now that we have a concept of chiral supercovariance, this is a left chiral supercovariant derivative, this is a right chiral super derivative, because that is spinor index undotted, this is spinor index dotted. That transforms under Lorentz transformation as half zero representation, this transforms under Lorentz representation as 0 half representation. Now with these things, we introduce a concept of a chiral superfield or a left chiral superfield, left chiral superfield. The superfields that we had listed earlier with 16 independent fields, that's the most general superfield we could construct in 4 dimensions. Now we will construct chiral superfields which are smaller than those, which means that the big one that we wrote earlier is made up of some irreducible set of chiral superfields, and we'll construct the building block chiral field, which is not any further reducible. So we consider irreducible set of chiral superfields, and to do that, we take a chiral superfield, call it phi now as opposed to f, which has the property, that covariant derivative, the anti-chiral covariant derivative, right-handed covariant derivative acting on this superfield is 0. This is equivalent to the condition that we had set up when we started constructing Wess-Zumino multiplet of fields phi, psi, f, and there we said phi does not transform under the barred supersymmetries. This is an equivalent statement. Is that this means this is equivalent to saying that phi transforms only under supercharged, unbarred supercharges, and we'll see some more detail of that structure. Now, a phi that satisfies this condition, we call it left chiral superfield.
So if I try to add the supercharges on this supermultiplet, so what should be the action?
Supercharges, you will see only the Q charges will transform it, and Q bar charges will give you.
Will the statement be that Q acting on phi commutator is 0 or anti-commutator is 0?
Depending upon what partner, this is
the Q bar I act on phi.
Q bar act on phi. We will do it epsilon times Q, which is a bosonic operator. So we'll always have commutators.
Oh, so you have to look at
yes.
Which components.
Yes. So Now, how do I construct this? To construct this, notice if I introduce an object called y mu, which is x mu plus I theta sigma mu theta. This is a shorthand for, again, theta alpha sigma mu alpha beta dot change the coordinate from x mu to y mu by adding this much amount to it. Notice this object is real. So we are adding a small imaginary piece to a real 4 coordinates. Not small, we are adding an imaginary piece. So introduce this complex coordinate. But this complex coordinate has the property that if I operate d bar alpha y mu on it, it is 0. So let me check that. So what is d bar? D bar is d bar alpha dot is this minus twice I not twice I. Where was this? I theta mu, call it theta nu, sigma nu, theta alpha, sigma nu, alpha alpha dot d nu. That's what it is. Is that right? And ecton now this spinel derivative acting on this doesn't give us anything. This is a theta bar derivative. Theta bar is here. So that gives me minus I theta sigma mu alpha bar. Little care, this derivative is with respect to dot in the alpha dot, it's a d bar. In order to hit this, I have to go across this theta. There will be a change of sign, so that makes it plus. Now let me operate at this object. This object does not operate on this because there is no x mu, it operates here, and you get an answer. This d nu acting on x mu gives me delta mu nu, that makes this nu into mu, and that's it. So these two are same. Not only that, if I operate d alpha, d bar alpha dot on theta beta, that is also 0. That's identically 0. Because this is a bar derivative. Bar derivative on this object is 0, and d nu acting on this object is 0. It has the same, yes. Now these properties tell us immediately how to write a chiral superfield. They tell us that this chiral superfield phi, which satisfies this, can be written as a function of y and theta alone, not theta bar. So at left chiral superfield is a function of y and theta, and by construction such a chiral field will satisfy this chirality condition, because both y and theta satisfy that. Now let me make an write a longhand expression for, or is that okay? Okay, so that's one. So I started with the superspace coordinates x mu, theta and theta bar. So then let me go over to new coordinates y mu, theta, theta bar. If I change coordinates from here to here, the supersymmetric algebra generators and the derivatives that covariant derivatives that I constructed will also correspondingly change, because I have changed the coordinates. What do I mean by that? Let's see how do these objects change under supersymmetry. Supersymmetry changes y mu, theta, theta bar as y mu goes to y mu minus, is that a minus or plus? Plus twice I theta sigma mu epsilon. Theta goes to theta plus epsilon. Theta bar goes to theta bar plus epsilon. It's straightforward to see that this is so. Y mu was x mu plus I theta sigma mu theta bar, and this would change under supersymmetry. X mu would change x mu plus I theta sigma mu epsilon bar minus epsilon sigma mu theta bar. That's how x mu transforms. And theta transforms as theta plus epsilon, and theta bar as theta bar plus epsilon bar. Right? Under supersymmetry, it's a translation in superspace. X transforms by this amount, theta transforms like this, theta bar transforms like this. Expand this out. Just expand this out. There are 4 terms, this one, this one, this one, and a term which has 2 epsilons, epsilon squares. So that's a higher order term. Combine this and this into y mu. Now look at these terms. This and this cancels, this and this adds up. So that's what it is. Y mu transforms as y mu plus 2I theta sigma mu epsilon bar. This is also bar here. So if I change from this basis to this basis, I ask the question, what are the supercharges that implement these transformations on these coordinates? That is, a supercharge would act as epsilon q bar q, let me call it y now, just to indicate that we are in the new basis, plus epsilon bar q bar y, acting on y mu, theta and theta bar should be twice I theta sigma mu epsilon bar epsilon bar. So a differential operator representation of the supercharges should act on these three in this particular way. So like I constructed the supercharges earlier in the x theta theta bar basis, I can construct now the supercharges in y theta theta bar basis. And if you do that exercise, you discover that qy, let me write down the answer, alpha is a simple object and q bar y at alpha dot is I times d bar alpha dot minus twice I theta alpha sigma mu alpha alpha dot d mu y. Just to remind ourselves that this is a derivative with respect to y and not x now. You can raise alpha by an epsilon, alpha dot by again epsilon, so the supercharges in this new basis y theta theta bar are these. And it's a straightforward exercise to check that algebra they satisfy is the same as the algebra of the supercharges earlier. But here is a y derivative with respect to y mu. So that was supercharges. Now we ask the same question about covariant derivatives. Can I construct a covariant derivative which is covariant under these transformations in the y space? Covariant derivatives d alpha y is d alpha plus twice I sigma mu theta bar alpha d mu y. If I raise it up, Now, look at the notes that you have. What has happened if when I change from x theta bar coordinates to y theta bar coordinates is that q alpha is the same as spinor derivative up to ni. But this object changes, essentially adds a factor of 2 here. That's precisely because this transformation is twice as much. Otherwise the same. Similarly for covariant derivatives. And these covariant derivatives also satisfy the same algebra. As supercharges. So now we have found a method of writing left chiral superfields. Left chiral superfields would be functions of only y, theta and y and theta only, no theta bar. And in the space of y and theta, various supercharges and covariant derivatives will be like the way we have written them down. Now write down most general expression for such a superfield. General expansion of left chiral superfield. Phi, we said phi is a function of only y and theta. So it could have a component which is independent of theta. So we call it small phi. And that would be a function of y. Then it could have a component containing theta. So we'll call it theta psi y. And just sneak in a normalization of root 2 here. Then it could have two thetas. Theta theta, and call that object f of y. And there can be no more, because I cannot write 3 thetas, because 3 thetas will have at least one theta component squared, and a component of theta squared is 0, because theta is our Grassmann coordinates. And to remind you again, this is the shorthand for theta alpha up, theta alpha down. And for sometimes I will also write it theta square. Now this is not the 2 component of theta. So from the context, please don't get confused with that. Because we used the same notation in sometimes earlier, saying that this is the 2 component of theta. Theta is made of 2 objects, and this is the component labeled by 2. But here, I'll use the notation sometimes that theta theta as theta square. By that I mean this object. And in terms of components, is theta 1 times theta 2. So such a chiral superfield is a collective name of 3 fields: a scalar field, a fermion field, and another scalar field f. By simple dimensional counts, if I give the scalar field, this object, first object, a dimension of mass 1, This is dimension of mass 3/2. This is a dimension of mass 2, dimension 2. Because thetas have dimension of theta is -1/2. That is also dimension of theta bar. That's very easy to read from the fact that this is a space-time coordinate y. Space-time coordinate is dimension mass dimension -1. Something added to it also has to be dimension -1. So both theta and epsilon. Epsilon we already had said earlier was dimension -1/2. So theta must be dimension 1/2. Sorry, this is not, this is transformation. So that's transformation. But even in the definition of y, how did we define y? This is mass dimension -1. So this better be also the mass dimension -1. So -1/2 in theta and -1/2 in theta bar. Now, it's useful to rewrite this as a function of x and theta bar. Because y is a function of x and theta bar. I could also rewrite this in a longhand as a function of x, theta and theta bar. So let me do it on the side here. Phi y is phi x plus I theta sigma mu theta bar, and make an expansion about it. Phi x plus I theta sigma mu theta bar d mu of phi x minus 1/2 theta sigma mu theta bar times theta sigma nu theta bar d nu of phi x. The Taylor expansion. I cannot write any more terms because then that can have, there are 2 thetas here, unbarred. That will have 3 unbarred thetas. 3 unbarred thetas will be 0. I thought we gave it an exercise that this whole thing can be written as half theta 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 bar theta mu nu. Was this an exercise? So if I write that, then this object is phi x plus I theta sigma mu theta bar d mu phi x minus 1/4 theta 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 bar d mu of phi x. Similarly, let me write root 2 theta y psi y as root 2 theta psi of x plus I theta sigma mu theta bar. That is root 2 theta psi of x plus I theta sigma mu theta bar of d mu psi x. Taylor expand this. There's a root 2 outside. There cannot be any more term because that will have cube of theta, 3 unbarred thetas. Now, again this was an identity. Here, and if you should be able to write root 2 theta psi of x. Use an identity to write it as minus I by root 2 theta theta d mu psi mu d mu psi sigma mu theta bar. We rearrange the thetas using various identities that we have done. You will get a factor of 1 minus half here and this object. Do the same expansion for f. And f has no more than the first term, because the second term will have at least 1 theta. So we rewrite this as now phi of x plus I theta sigma mu theta bar d mu of phi of x minus 1/4 theta square theta bar square d mu phi of x plus root 2 theta psi of x minus I by root 2 theta square d mu psi sigma mu theta bar plus theta square f of x. Now this chiral superfield written as a function of y and theta has this expansion, but instead if I wrote it as in terms of x and theta bar, it has this long expansion. Now if you look at this object, this looks similar to the general chiral superfield we wrote, except that some of the terms are absent. See, now I have used the shorthand this here, theta 2 is theta and theta bar square is theta bar. So that was just to give you a feeling about is that this compact way of writing is really a longhand expression for this. And it would have been difficult to discover that this is a chiral superfield in this language. It's so easy to do it in this language because by construction it's so. Now let's ask the question about what happens to this left chiral field under supersymmetry transformations. SUSY transformations on phi y theta. Phi y theta would change into a phi y plus or minus plus 2I theta sigma mu epsilon bar theta plus epsilon. Y changes under supersymmetry by this amount, theta changes by this amount. And now let me just make it a tailored expansion of this around y and theta. What do I get? Phi y theta plus 2I theta sigma mu epsilon bar d mu y of phi y theta plus epsilon bar d alpha of phi y theta. phi at y, and this is the expansion with respect to y. Change and derivative. Phi at theta, and this is the expansion with respect to theta. Epsilon times. Should I do this exercise, or you can do it? Now you write phi as this object and rewrite all these terms. Del? This one, have I missed something?
Del alpha y.
Well, this is ordinary spinor derivative, ordinary. It's not a covariant derivative.
Sorry.
This is spinor derivative, so it acts on thetas. This is x on space-time,
Yeah,
so it is y. So you do this and do a little bit of phase rearrangements, and you should be able to get the answer that this is phi, small phi, this one, plus root 2 epsilon psi y. This piece comes from here. When d alpha acts on this object, it just peels off this theta. So you have root 2 times psi y times epsilon. That's this. Plus this is the term, this term that will come from here. Then look at this piece and take this derivative on psi. No, not sorry. Take this piece acting on this object. That has a single theta. So this is a single theta, and do the phase rearrangements, and you discover the answer is plus root 2 I sigma mu epsilon bar that is this acting on this. Then take this one acting on this. That will peel off one theta and leave one theta. That's single theta term. Now collect the two theta terms. One will come from f component of this object. Second will come this derivative acting on the second component of this object, derivative of psi. That will have two thetas. One theta is here and one theta is here. Do the phase rearrangement and convince yourself that it is minus root 2 I d mu y of psi y sigma mu epsilon bar. nothing but this expansion. Now this is the transformed superfield, and we can write this now as the transformed y component, the theta-less component of this object, root 2 times theta transformed y component plus theta theta transformed the y component, a f component. So now this tells us that supersymmetry acting on these chiral superfields changes the various components phi in this way, psi in this way, f in this way. This implies change of phi is this is the change in phi. I have replaced y by x now. I can do that.
In that is the one term missing, so delta of phi n, theta of f, the second transformation.
This one?
Yeah.
Oh yes, yes, you're right. You're right. Very important term. Where is that? Didn't I write it?
Yeah. Theta of f.
I have missed it here. Yeah, this one. Yes. This is there's something missing. I have missed an epsilon here. There should have been an epsilon here, right? Epsilon f of x. Because this epsilon, because one derivative, this epsilon should have been there. So this is epsilon, that's what it is. It's theta times theta, epsilon. This is what it is. Yes. Now what's this? This is exactly the supersymmetric transformations that we had found earlier for chiral supermultiplet, scalar supermultiplet. Same transformation rules as were found earlier for scalar supermultiplet or chiral supermultiplet. There's a root 2 also somewhere hanging here. Huh? Epsilon has a root 2 also here. Huh? Now this will also tells us the power of superfield techniques. It gives you a systematic way of finding out representations of SUSY algebra. Now what I could do is that I took this to be the left chiral superfield, which was a superfield which was killed by the covariant derivative, the barred covariant derivatives. I could equally well considered a chiral superfield which was killed by the unbarred covariant derivative. So the anti-chiral superfield or right-handed superfield. And let's give it a name, call it phi dagger. Now phi dagger has the property that d alpha acting on phi dagger is 0. Notice, if I construct a new coordinate, call it y bar, which is x mu minus I theta sigma mu theta bar. This is minus as compared to y that I introduced earlier. In fact, this is conjugate of that y, because we said this is real. It changes the sign of the imaginary part. Now this object has the property that d alpha on y mu is identically y mu bar is identically 0. Check it the way that we did it for y. D bar acting on y was 0. Now d unbarred acting on y bar is exactly 0. Now d acting on barred coordinates is 0. So what it tells me is the same argument again, that an anti-chiral superfield I can write it as a function of y bar and theta bar. So this implies that phi dagger is a function of y bar and theta bar. And if I were to write its components, call the lowest component without thetas as phi star root 2 theta bar y bar y plus theta theta bar bar f star y. Now under SUSY, how do these y bars change? This can be checked directly because we know how x change, how theta change, how theta bar change. Do the same exercise that we did earlier. You will just discover that this is, it is the piece there survives here is the one that cancelled there for the y. Now exercise under SUSY phi dagger y bar theta bar changes to phi dagger y bar minus 2I epsilon sigma theta bar plus epsilon bar, and make an expansion, Taylor expansion of this object, and find out how do the various components of the antichiral field transform. Show delta phi star x is root 2 epsilon bar phi x bar delta psi bar x is minus I root 2 epsilon sigma mu d mu plus root 2 epsilon bar f star x It's a straightforward exercise, just a repeat of that exercise. And this is also what we prescribed last time for antichiral superfield. And if we, like there, for the chiral superfield, when we change the coordinates from x to y, we also change the differential operator representation for SUSY algebra and also the covariant derivative. So SUSY differential representation that implements this transformation, that y bar mu goes to y bar mu minus twice epsilon sigma mu theta bar. Do I have it? Yes. And theta goes to theta bar, theta plus epsilon. Theta bar goes to theta bar, epsilon bar. There is a corresponding construction of q bar y bar alpha. So q y bar alpha, q bar alpha dot y bar, and there is also a construction of covariant derivatives y bar which is parallel to what we did earlier. I will not do that here.
Is there something like charge conjugation and quantum field theory here also, that you can move from this to this and vice versa?
Yes, they are charge conjugates of each other.
Going to the y form can give us this transform, changing the frame from x to
y gives you a quick way of doing it. Otherwise, you would have to, it's still here. Otherwise, you will have to write it in such a long way and then make sure what implements supersymmetry transformations on these fields and discover it that way. That would be an inefficient way of doing it. You can do it. Yes. So now how we have learned how to construct left chiral superfields, right chiral superfields, and we have also learned how to use their structure and their properties to extract out how a chiral supermultiplet of fields transforms, or how an antichiral supermultiplet transforms under supersymmetry. Now, all these transformations have some properties And this is a property which I pointed out earlier also, and let me repeat it now. F derivative, F term of these superfields. F term is the term that comes with 2 theta coefficient. Did I write it here somewhere? Here. 2 theta or 2 theta bars. For chiral fields, it will be 2 thetas. For anti-chiral fields, 2 theta bars. That is the F term. And this term in both cases is dimension 2, mass dimension 2. And in both cases, it transforms as a total derivative. So F terms transform as total derivatives. So this is comment 1. F terms of a chiral superfield or an F star term of anti-chiral superfield transform as a total derivative. So F term, what is the F term? Of a chiral superfield, take the chiral superfield Y, it's a function of Y and theta, and take the F term, which is take the theta component of the superfield, and after that put theta equal to 0 and theta bar equal to 0. What will that do? That will convert Y mu to X mu. Because when theta is 0, theta bar is 0, X mu and Y mu are same. They differ only by a piece that depends on thetas. So take the theta component of this object, and whatever that theta component of object is, in that put theta equal to 0 and theta bar equal to 0, because that depends on Y, and Y has theta bar. That to convert it to be a function of X. Similarly, take the anti-chiral superfield, take the F term. F term is the coefficient of theta bar term, and convert the dependence on Y bar to an X dependence. We'll do it many times, but I will not say it again in words. So this is, I'll just shorthand write this object, phi x is this object. So I will not say it again. What I have done is that I have done this. I have taken Y going to X limit. It should be understood in the context. I will maybe specify sometimes, but sometimes I may not. So that's one nice property. Second nice property is that product of 2 chiral superfields is also a chiral superfield. So if I take phi 1 chiral superfield, so it depends on only Y and theta, and take another one phi 2, which also depends on Y and theta. That means both of them satisfy d bar alpha dot by construction, because they are functions of only Y theta. Then the product superfield Take the product of two superfields. Now phi 1 y theta in the long hand I can write as phi y root 2 theta psi 1 y theta theta f1 of y, and phi 2 y theta as phi 2 y root 2 theta y theta theta f2 y. Now, this is a function of y and theta, this is a function of y and theta. Product is also a function of y and theta. Therefore, by definition, by construction, it's also a chiral superfield, which means d alpha, bar alpha acting on this product is also 0. Now, since it's a chiral superfield, I should be able to write an expansion of this chiral superfield in terms of a theta less term, one theta term, and two theta terms. So I just take the product of these objects and construct that expansion. Now what do I have here? Theta less term is phi 1 y, phi 2 y. That's simply the product of these two terms. Then what is the single theta term? Single theta term is phi 1 times psi 2. And phi 2 times psi 1. This times this times this single theta term. Root 2. And what is square theta square? Theta square is, one is this times this, other is this times this. But there is one more term which is this times this. So there is also a term 2 theta psi 1 y theta psi 2 y. Write this as 2, is it 2 or, yeah, 2, right? Yes. Theta alpha psi 1 alpha theta beta psi 2 beta. Take these across 2 theta alpha theta beta psi 1 alpha psi 2 beta. Now this object, there is an identity that this I can write it as, I am minus 2 as half epsilon alpha beta theta theta. And I think there is a minus sign here. Yes. So that makes it theta theta epsilon alpha beta psi 1 alpha psi 2 beta. Rewrite this as theta theta epsilon beta alpha and put a minus sign here. Because you have interchanged alpha and beta. Now by this definition, alpha alpha contracted here, this raises the index. that gets killed by this half here. All right. So this tells us, this gives us rules of how to write product of two chiral superfields. And now this is the product chiral field with the first theta-less component as this one, single theta component as this one, fermionic component, and two theta component, this one minus this one. Now this was discussion about product of chiral superfields. The same discussion will hold for product of anti-chiral superfields. Product of anti-chiral superfields. Phi 1 dagger, which is a function of y bar and theta bar, and phi 2 dagger, which is a function of y bar and theta bar, is also an anti-chiral superfield. By construction. And how would the various components of this object will be? Something of this kind only. We learnt this property, that the f component of a chiral superfield always transforms as a total derivative. Now I have constructed a product chiral superfield whose f component, the theta theta component, is this combination. It's phi 1 f2, phi 2 f1, and psi 1 psi 2. So then this combination together also will transform like a total derivative. Right? So now we have found, earlier we found a simple field which transformed like a total derivative. Now we have found a complicated expression of fields which transforms like a total derivative. This is the kind of a trick we'll use in writing a more and more complicated objects which will transform like total derivatives. And finally, we can write action in terms of such objects, because action that transforms under insymmetry by total divergence, the Lagrangian density transformed by total derivative, action is invariant. So we already started seeing the rules of constructing supersymmetry invariant Lagrangians. Now there is an exercise. Show that f term of the product of three chiral or anti-chiral superfields is, so you take a chiral superfield phi 1, take another chiral superfield phi 2, and a third one phi 3. It will have all terms, but write down the f term. F term is the theta theta term. This remarks I made earlier already suggests that f term has some special roles. So therefore we are interested in figuring out how to compute f terms in a product of chiral superfields. In fact, you have already found out how to take the product of two chiral fields. Just multiply by one more chiral field, and that is again now product of two chiral fields only. So you just have to use the same rule that you have here in order to get any product of that kind. So check the answer is the following: f1 phi 2 phi 3, f2 phi 3 phi 1, f3 phi 3 phi 2 minus psi 1 psi 2 phi 3 minus psi 2 psi 3 phi 1 minus psi 3 psi 1 phi 2. It's almost just reading off from here. I have all two phi, product of two phi's here already, just multiplied by third phi. So what do I have here? I is the first component of the first one times the f of the second one. Now the first component of this product one is this term times the f of the third one, f3. That's this term. No, something is not. 3, 2, 1. 3, 1, 2. Cyclic. So that's this term. And similarly, you can construct all of them. And for conjugate ones, F1, you just star everything, F1 star, F2 star, F3 star, F2 star, F3 star, F1 star, F3 star, F1 star, F2 star, minus psi 1 bar, psi 2 bar, F3 star, psi 2 bar, psi 3 bar, F1 star, F psi 3, psi 1. Now this was product of chiral superfields. Now what about a product of a chiral and an anti-chiral superfield? Product of a chiral and an anti-chiral superfield. So you take phi 1 of y theta and phi 2 of dagger of y bar theta bar. Clearly it's not a chiral superfield. Is not a chiral superfield. So I have dagger here and this is undaggered, so this is. But what you can do is do this exercise, take phi 1 dagger y theta bar bar and phi 2 y theta, write them in components and make the expansion and pick up a term theta theta and theta bar theta bar. See, write this object as phi 1 dagger y theta as phi 1 star y bar root 2 theta bar psi bar y bar plus theta bar f1 y star y bar and phi 2 y theta as phi 2 y root 2 theta psi 2 y theta, theta, phi 2, y. Okay? And then take the products. And do this is a long exercise. After you take in the products, write y as a function of x and y bar as a function of x and pick up this term. This is the interesting term in this product, so that's why only this term. What is the structure of this term? That's straightforward. All functions of x, which means after taking the product, you expand y around x and y bar around x, and then pick up terms only with these coefficients. You will discover this is the answer. Now this term is also interesting. This term is interesting because in the general chiral superfield that we wrote, we had given a name to this term. We had called it D. So this is called a D term. Coefficient of theta, theta, theta bar, theta bar. That's the name of this term. For the chiral fields, the coefficient of theta, theta we called F term. F was given the name for that. This is given D term. D term of a superfield always transforms as a total derivative. So what we have learned? We have learned that F term of a chiral superfield transforms as a total derivative, and D term of a general superfield, which could be constructed from products of chiral and anti-chiral superfields, also transforms as total derivative. So therefore, we can use these two pieces of information to construct a supersymmetric invariant Lagrangians. That we'll do next time.